All right, so this is the beginning of chapter 4, which is about aqueous chemical reactions. So we need to talk about chemical reactions first. So we need to, in general, talk about how chemical reactions are set up, and more importantly, how we write them and how we keep track of things. Okay, so I'm going to work through an example and just kind of point out a few things here. So one example is if you take potassium, which is a column 1 element, it is a solid, and if you throw it in water, which is a liquid, these little symbols are called the state symbols, what will happen is it will violently catch on fire, and the products will be KOH, which is aqueous, which we'll define what that means in a minute, and H2, which is gas, basically hydrogen gas. Okay. A couple things to point out here. The left side of this arrow is called the reactants, and we will refer to it as such throughout this entire semester. The right side of this is called the products. Okay, so these are the things that are reacting, these are the things that are produced during the reaction. Okay, this little arrow just means some sort of chemical change. It's super vague. Occasionally you'll see symbols written over top, or like it'll be like at a certain temperature or stuff like that. You can, like if you have a catalyst, this is where you would write it, but for most of the things we're going to do, the arrow just means some sort of chemical change. Okay. One thing we're going to need to deal with pretty soon is the idea of balancing chemical reactions. The idea is, since matter can't be created or destroyed, since chemical reactions are essentially the same idea as literally like Legos, like they're combined in a certain form here, you rip them apart and reorganize them over here. You're not creating or destroying any atoms, you're just rearranging how they're connected. So we should have the same number of potassium, hydrogen, and oxygen on this side as we do on this side. I'm going to quickly balance this one, and then most of the rest of this video is going to be me explaining how to do that. Okay, so we have one potassium, everything great. 2 hydrogens, 1 hydrogen plus 2 hydrogen would be 3 hydrogens, so that ain't gonna work. So I'm gonna increase the number of hydrogens over here. I'm gonna try putting a 2 here. That will now give us 4 hydrogens, and we still only have 3 here, but we've also doubled the number of oxygens, so I'm gonna put a 2 here to give us 2 more oxygens, but that unbalanced the potassium, so I'm gonna put another 2 here. Now we have 2 potassiums on both sides, 4 hydrogens, there'd be 2 here and 2 here is 4, 4 on this side, 4 on this side, and 2 oxygens and 2 oxygens. I'm going to teach you how to do this later. I do not expect you to be an expert yet. Real fast, I also want to define these little guys in parentheses. Not every single equation you'll encounter has these things in parentheses. They're called state symbols. They are common enough, though, that you should probably know what they are. Okay, so most of these are fairly obvious. S means solid. L means liquid. I write my L's in cursive in here. You don't have to. I'm only doing it because my L's typically look like 1s, and there's enough letters and numbers floating around together that I need to distinguish it. G is gas, so solid, liquid, gas. Those seem like the really obvious ones. They're the 3 main states of matter that we encounter in chemistry. Plasma is technically an option, but we're going to ignore it. This AQ one, which I kind of wrote poorly, stands for something called aqueous, which is the first word of our name of our chapter. So aqueous means dissolved in water. We're going to go into excruciating detail about what that means probably in the next video, but for right now, we're going to worry about how to balance things. So these little state symbols they can be important, but they're not always in every chemical reaction that we deal with. Okay, so we need to talk about how to balance chemical reactions, how to get these numbers in the front that are all the same. Okay. Balancing chemical reactions is not actually that impossible. It just requires you to be really diligent and tedious about everything, like a lot of things in chemistry. So the idea is there has to be the same number of each element on each side. By each side, I mean the reactant side and the product side. Okay. You can't change any of the subscripts. So the only thing we can do is add numbers in the front, and they have to be nice whole numbers. And I'm going to say that, and then literally in about 2 chapters, we're going to use fractions a lot. But for this chapter, we're going to get nice whole numbers every time. Okay. Those numbers in the front are called stoichiometric coefficients. It sounds like a really complicated term. So we can only add numbers in the front. Those are called stoichiometric coefficients. I will occasionally refer to them as coefficients, but usually I just say the numbers in the front. Unfortunately, there's about 10 ways to do these. I'm going to show you what I think is the most systematic approach, the one that students seem to respond well to, and we'll kind of go from there. In class, obviously, if this is not clicking, I could try to show you some of the other options. So, for example, if we had something like C3H8O2 forming CO2 plus H2O. This is an example of something called a combustion reaction. If you take an organic compound and you react it with oxygen, you almost always, well, the only products you ever get are CO2 and water. Pretty much any compound that reacts with oxygen and basically forms fire is a combustion reaction. So this also works with like magnesium, works with a lot of metals. So the way I tell students to do this is do an inventory of what you have on each side. So we have carbons, hydrogens, and oxygens. That's not the order they're in over here, but I'm going to write it in the same order just to make it easier to compare things. Okay, on this left side, we have 3 carbons, 8 hydrogens, and 2 oxygens. On the right side, we have 1 carbon, 2 hydrogens, and there's 2 oxygens here and 1 here, so that's 3 total. Our goal is to add coefficients in the front until all these numbers are the same. Okay, I fully admit that if you added zeros in the front, they would all go to 0 and it'd be super easy. We don't have that option. They have to be nice whole numbers. So I literally just do it. I pick one element at a time and I fix it one element at a time. So we have 3 carbons on this side. We need 3 carbons on this side, so I'm going to put a 3 in the front. This will change these numbers. So every time you add a number, you have to refigure this up. So carbon, we had 1, now we have a 3. This 3 applies to everything in the molecule, which means we have also unbalanced our oxygens. We have 3 times 2 is 6, plus another one here is 7. We'll deal with that in a bit. That's fine. Hydrogens. We have 8 on this side and 2 on this side. So these come in packs of 2. Every molecule has 2 hydrogens in it. So if we had 4 of those, 4 times 2 would be 8. But we also messed up our oxygens. This is 6, and then another 4 would be 10. Okay. We have 10 oxygens on this side and 2 on this side. They come in packs of 2, so putting a 5 in the front will give us 10. 3, 8, 10, 3, 8, 10. It's the same. We have balanced this. Okay, literally you just have to go back and forth until everything's balanced. Okay, let's try a couple more, just to make sure we've got at least a handful of them in your notes. See some examples. Okay. How about, this one's probably pretty easy. We'll start with that. Okay, so lithium we have 1, Aluminum, we have 1. Chlorine, we have 3. Same elements on this side, and we have 1 of each. So really the only thing that's messed up on this one is the chlorine. We have 3 on this side and 1 on this side, so we have to put a 3 in the front, and that changes that to a 3, but it also messes up our lithiums. Now we have 3 on this side and 1 on this side, so we need a 3 here also. You'll note this one was notably easier than this one, but it's the same logic. You still just bounce back and forth one element at a time. We never even touched the aluminums. They were 1 on both sides. We didn't do anything. Okay, let's try another. Okay, you'll probably find that balancing things isn't that difficult. Accurately counting things along the way actually is the hardest part. So this one, we have aluminum, oxygen, hydrogen, and sulfur. We have oxygen, hydrogen, oxygen, hydrogen, sulfur. I'm going to put them in the same order on this side. So on this side, we have 1 aluminum, we have 3 oxygens here, and 4 oxygens here is 7. We have 3 hydrogens here and 2 here is 5, and 1 sulfur. On this side, we have 2 aluminums. Oxygens, 3 times 4 is 12, plus another one is 13. Hydrogens, we have 2, and sulfurs, we have 3. Since there are lots of hydrogens and oxygens everywhere in this, I'm actually going to ignore those until the end. I'm going to do the aluminums and the sulfurs first. So, aluminums, we have 1 here and 2 here, so I'm going to put a 2 in the front. That unfortunately messes all these numbers up and we have to recalculate them. That's okay. So, oxygens, 2 times 3 is 6, plus another 4 here is 10. Hydrogens, 2 times 3 is 6, plus another 2 is 8. I'm actually going to skip ahead and do the sulfurs now, because hydrogens and oxygens are going to change pretty much anytime we do anything, so we might as well fix everything else first. So, sulfurs, we have 3 on this side and 1 here, so we need a 3 in the front. And that screws up our hydrogens and oxygens. Okay, so oxygens, we have 2 times 3 is 6, 3 times 4 is 12, 6 plus 12 is 18. Math working here? 3 times 4 would be 12, plus another 6, 18, yeah. Hydrogens, 2 times 3 is 6, 2 times 3 is 6, so we have 12. Okay, so our goal right now is to balance, we've got the all aluminums and the sulfurs balanced, we need to balance the oxygens and the hydrogens. Since there is an oxygen in every single one of these, I'm going to try to balance the hydrogens next. We have 12 hydrogens on this side, they come in packs of 2 over here, so I'm going to put a 6 in the front. That will give us 12. It will also mess up our oxygens. Here we have 4 times 3 is 12, plus another 6 is 18. So it actually took care of itself, which is good because we didn't have anything else we could change without messing up hydrogens, aluminum, or sulfur. You'll note this one required way more counting. It was a little more detailed, but it's the same skill set over and over and over and over again. Okay. Let's try another one. Ca3PO4 2 plus SiO2 plus carbon forms SiO3, supposed to be Si, sorry, plus CO plus phosphorus. So we have more compounds this time. Okay. I'm actually going to argue that you don't have to write all this little inventory thing. You can just do it as you go. You just pick one element at a time and worry about that. So calciums, we have 3 here and 1 here. So I'm putting a 3 in the front. Silicons, we have 3 here and 1 here, so I'm putting a 3 in the front. Phosphorus, I am, I guess, ignoring for right now because I can easily fix that at the end without a whole lot of effort. Okay. So carbons, we have 1 and 1, so we're good. Let's try to fix the oxygens. On this side, we have, well, this is 8 plus 6 would be 14. On this side, this is 9. 9 plus 5 would be 14. So we need a 5 here, which gives us 5 carbons. So now we need 5 carbons here, 2 phosphorus, 2 phosphorus. Sorry, my handwriting got sloppy on that one. But it's the same process, I just didn't have to write all this out. Some people struggle to do this without writing out all the inventory stuff. If you have to do this, that's totally fine. I just got lots of practice. Okay, let's try a couple examples that use the only weird glitch that I know in this stuff. Okay. So NH3 plus O2 forms N2 plus H2O. And this looks like it should be straightforward and easy. And it's not horrifying, but it does require a weird little trick. So I'm actually going to write all this out just to show what's going on here. So we have 1, 3, 2. Here we have 2, 2, 1. So I am actually going to balance the hydrogens first. And it's because no matter what we do, the hydrogen number is going to be a little weird. Okay? Actually, let's balance the nitrogens first. It probably seems like the first logical thing to do. So we have 2 on this side, we need a 2 here. It'll probably fix my hydrogen problem that I was talking about. So we doubled all that, so we need 6 of these. We end up with 6 hydrogens on this side, so we need 6 here. That'll give us a 3 here, which gives us a 6. And now that gives us 3 oxygens. Here's the problem. The nitrogens are balanced, the hydrogens are balanced, the oxygens are not. We need 3 on this side, but they only come in packs of 2. So here's the trick. This is the only trick I know out of the entire process. We need 3 on this side. I'm going to write it as 3 halves, because 3 halves times 2 equals 3. So technically this gives us 3. Here's where the problem is though. We're supposed to have nice whole numbers here, and this is a fraction. So if this is balanced, which it is, and we doubled everything, as long as we double everything consistently, it should still be balanced. So I'm going to double everything. This will become a 4, a 3, and this is a 1. If you don't write anything, it's assumed there is a 1 there. 2, and 6. Okay, that little doubling trick is as close to a trick as I know in balancing things. Honestly, most of the time, it's pretty straightforward like the previous ones. We will do more examples in class, but this is the gist of how to do balancing chemical equations.